Welcome back everyone to another lecture for second year physical chemistry, and today we are going to talk about ionic activity. What will be covered and why? Activities, or the parameters that capture real behavior, for ionic systems are different to non-charged systems due to the large electrostatic forces involved. Thus, we are looking at it separately. What you will need. Atkins is physical chemistry, simple mixtures, activities, and previous lectures on chemical potential. Activity coefficients for ionic systems. So far we have dealt with systems that are not charged, but what if we have, say, a dissolved salt in a solution? And for example, if we decide to dissolve some table salt, sodium chloride, into water, we would expect that the charge on an ion is a source of non-ideal behavior, since the like charges repel and unlike attract. Now, if we had 1 molar sodium chloride in water, and if you work through the calculations and trying to discover what the average force would be for one positive charge, say a sodium ion and a chloride anion, what the average force between the two would be for a 1 molar solution, you would get a ridiculously large number, such as 10 to the 29 newtons. That is enormous. There's a lot of energy in that. The question is, why then are salt solutions not that highly energetic? What happens, of course, is there's not just one ion of each in a solution. There are a molar quantities. Hence, what you'll find, for example, if you look at the image on the right, a positive charge would be surrounded by negative charges, such as to cancel the overall force on that positive charge to be a net zero. However, because fluids are quite mobile, that net zero does fluctuate over time. And because it fluctuates over time, just sometimes you will get these large electrostatic forces starting to interact and exhibit themselves. And it exhibits themselves in the form and can be parameterized in the activity coefficient. Alright, with that out of the way, we can immediately write down a basic form of the salt chemical potential. Chemical potential is equal to the standard state chemical potential plus RT log gamma x. We should now be familiar and quite happy with this. And naturally, we can rewrite this in terms of the ideal component and the non-ideal component. So the chemical potential is equal to the ideal chemical potential plus RT log gamma, the activity coefficient or the real part of the chemical potential. However, there is an important subtlety to consider with ionic systems. Let's use the Gibbs-Duhem result to write down the Gibbs free energy of a solution of NaCl, right? In fact, it doesn't have to be sodium chloride. It could be any other simple salt like calcium chloride or some such. We have the Gibbs free energy. G is equal to the number of moles of the cations times their chemical potential plus the anionic component. And as you can see, positive is for the cation, negative is for the anion. Since the number of moles of anions and cations are the same in a sodium chloride solution, we can divide the Gibbs free energy to obtain the molar Gibbs free energy, so which we denote with M. And you'll follow the derivation and you'll note that the molar Gibbs free energy can be split into two parts, the ideal component and the non-ideal component, which is RT log gamma minus times gamma positive. Now here's a key question. Can you measure the activity of an anion separately from a cation? What I want you to do is to pause the video and think. Is it yes or is it no? If it helps, pause, write down the answer and the reason why. The answer is no. Why? Because you can't take out the anions and leave only cations behind. This is energetically impossible for reasonable amounts of materials. Systems obey charge neutrality. You want a solution in the end that is positive, overall neutral. So what do? So here's our molar Gibbs free energy for an ionic solution. What do? We take what is known as a geometric mean. And this is how we define it. That the square root of gamma minus times gamma plus is equal to gamma plus minus. So this entity we can put into our chemical potential. For example, the cationic chemical potential. We've got the ideal component plus RT log gamma plus minus. All right, so the above was a simple case for a very simple salt. What if you have salts with different charge to them? For example, calcium chloride. There's one calcium cation, I mean, 2+, and then you've got chloride minus ions. So, what do? You rederive the entire thing, and then you redefine a new geometric mean for the activity coefficient, which you can see is the definition here. Gamma plus minus is equal to gamma plus to the power of P, and gamma minus to the power of Q, and you take the root to the power 1 on S, where S is just P plus Q. So, key takeaway today is the source of non-ideal behavior in ionic systems is due to their charged nature. And one cannot separately measure the activities of anions from cations, since both are required to be in close proximity with one another to maintain charge neutrality. Activity, thus, for an ionic system is a geometric mean. And so there's your equation, and hence we can write our chemical potential for an ion as, for example, the cation, the ideal component plus RT log geometric mean activity coefficient. Alright, now for the quiz. Question 1. Can you determine the activity of an ionic solution via the vapor pressure of the solvent of the system? Yes or no? Question 2. For a salt such as calcium chloride, the activity coefficient for the calcium and chloride ions are the same or different?